engine ignition. 4, 3, 2, 1, 0, and liftoff.
Ever notice shuttle launches happen at all hours? Some are during the day, some at dusk, some in the middle of the night. Ever wonder why? Well, there's a lot of math that happens in order to figure out what time the shuttle takes off. So get out your calculator and we'll show you how to come up with a good time for liftoff. Next on Real World. One of the most important missions of the space shuttle is to deliver astronauts and material to the International Space Station. Seems pretty easy, right? But it's a lot more complicated than typing ISS into a GPS and taking off. The International Space Station, or ISS, is in orbit around the Earth, and for the space shuttle to catch up and dock, well, it's a lot trickier than it sounds. The lesson starts with gravity.
If we go around the Earth or any other planet or heavenly body, there's gravity that's going to pull us to the middle of it wherever we go. And in any orbit, all that we end up doing is we go fast enough sideways that we just truly fall over the horizon.
Dr. John Bacon is a systems integration engineer for ISS at NASA's Johnson Space Center.
Near Earth, we have to do it at about 8 kilometers a second or 5 miles a second. We get up above the atmosphere and we just stay in a continuous circle going around the center of the planet. Imagine a plane, a flat sheet that goes right through the planet. We draw a circle on it and that represents our orbit. And that sheet is called the orbit plane. Now, we don't always go right around the equator, and in fact it's quite hard to do that from the Kennedy Space Center here. What we have to do is go around the center of the planet. So we have to get into an orbit that inclines around the planet so that it goes over the Kennedy Space Center. That plane has to be centered on Earth's center and has to go over the Kennedy Space Center somehow.
So the space station is traveling along its orbit, on its orbital plane. We know that an object's orbit is fixed in space. It follows the same path over and over. At the same time the ISS is orbiting at nearly 28,800 kilometers per hour, Earth is rotating at a speed of 1,665 kilometers per hour. If the ISS passes over the Kennedy Space Center during one orbit, the Earth will have rotated about 22.5 degrees in the 90 minutes it takes the station to make another orbit, putting the path of the ISS about 1,600 kilometers west of Kennedy. To find out how long it will take to pass over KSC again, we need to divide the circumference of Earth, approximately 40,000 kilometers, by the speed of Earth's rotation, approximately 1,665 kilometers per hour. And we see that the ISS will pass in the correct spot only once every 24 hours.
We have pretty open ocean heading up to the north, and so we always like to head out into orbit on the pass that sends us over the Kennedy Space Center, heading from south to north. This happens once a day.
So, if it's launch day, that is the moment the shuttle would launch.
So we get this very narrow window of time when the Kennedy Space Center is under the disk that's being made by the space station. And that's called our launch window.
But once launched, and in orbit, it still has to catch up to the space station.
Now, the shuttle only has a limited amount of resources on board. It can stay in orbit for about 17 days, and we'd like to spend as many of those days as possible docked with the space station.
Once in orbit, the shuttle travels at the same speed as the International Space Station, 28,800 kilometers per hour. But if it's traveling at the same speed, how does it catch up? By traveling on an inside track.
Here to demonstrate this concept is Maddie and Elise. Maddie will represent the International Space Station and Elise the Space Shuttle.
The shuttle, like a runner on the inside track, will eventually catch up with the station, represented by the runner on the outside of the track, provided both are traveling at the same speed. It's because the inside runner is covering a shorter distance over each lap. Checking the numbers, it's 400 meters around the inside lane of the track. But in lane 8, 456 meters. So a runner on the inside track will circle the track in a shorter time than a runner on the outside track, when both are traveling at the same speed. The shuttle and the station work like the runners. The shuttle, on the inside of the orbital plane, will eventually catch up with the space station. That's when docking occurs. To get the most of their resources, NASA launches so the shuttle will rendezvous with the station within 2 days. And as for the different launch times, well, that's got to do with the Earth and physics.
Because it has a soft molten core and it is spinning, it tends to flatten out. It gets the poles a little bit closer to the center than the equator. It bulges out.
That bulge creates gyroscopic effects on the orbital plane.
Just like a gyroscope, it starts to precess.
Precess is the change of direction of the axis of rotation of a body caused by external forces.
Now, what does that mean to us at the Launch Center? It means that if we are ready to launch at 7:30 in the morning on any given day, the next day that orbit plane will have twisted enough that we have to launch 23.5 minutes earlier.
By understanding orbital mechanics, scientists and engineers like Dr. Bacon can use known variables, such as the distance of the ISS from the center of the Earth at any given time, the satellite's velocity, and the diameter of the satellite's orbit, to launch the shuttle and make orbital changes so it will rendezvous with ISS at a specified time. So, as you can see, a lot of thought and a lot of calculations go into every shuttle launch. Learn more about launches and all of NASA at www.nasa.gov.